So I haven't yet managed to talk to Shubi Sharkar, okay, in Shah Institute. I'll talk to him, okay, I mean, either today or tomorrow, and I'll ask him, okay, to prepare something, okay, I mean, essentially which version of Geant4 would be good. I think don't go for the most recent one, okay, go for a slightly older version, and he will try to say, okay, I mean, how it can be installed on a Linux platform. So I think, okay, so but which platform I really do not know. What is his most favorite? I mean, what Linux thing? Okay, I mean, he uses. Okay, I can't say offhand, but it's definitely it's not a Mac. It is something which you can do on a other computers. Okay, so we talked about the sensitivity detectors, okay, last time, okay, and the sensitivity detector is a place where you store information in the during the time of simulation, and this information are stored in the form of units, which is called a heat. And what Geant4 provides is basically provides a virtual class. It's a purely abstract class, and one really has to inherit that particular class, okay, to give a concrete G4 heat class for doing that. So it is a information one has to get from the step information, and essentially record it, okay, into something which is called a heat correction, and that is stored in the event. And at the end of the event, okay, I mean, you still have this heat collection class, so you can access this information, okay, from that heat collection class, and finally you write output of that, okay, into your wherever you want. Okay, I mean, it's a where you do the analysis. Okay, so that's the whole idea. Now the heat collection, okay, could be, okay, this is also covered, okay, I mean, it could be a pure correction class or it could be a map class. Correction means, okay, it is a vector of heats, and the map class is essentially a map of heats. So these are all are templated class. So you can use either the G4T heats collection, okay, or G4T heats map, okay, and then you store that information in those things. So far we have only done that. As I said, okay, heat is a totally user-defined class derived from G4V heat, and the user can store various types of information by implementing one's own concrete heat class. So as I said, okay, it could be have information like the position and time of the step, okay, which you can derive from the step, the momentum and energy of the track in that particular step, energy deposition during the step, some geometrical information, or some combination of this. And as I said, okay, I mean, you have to make a concrete class for the heat correction as well, and then you store that thing in that particular heat correction object in that thing. Okay. And this I also already said. So this heat correction is accessed in two places. Obviously, during the sensitivity detector, you have stored this information in this heat collection, and at the end of the event, okay, I mean, you access the information from the heat collection and take this information and store somewhere else. Okay, so that's the whole idea. So this is the way, okay, I mean, you normally try to implement a particular heat class. You can see, okay, this is a publicly inheriting the G4V heat, and then you really have to implement. Well, I think there is no need, okay, to implement this, but the thing is, okay, I mean, what you really want to implement is something by where you store your private information and how you can access those private information through some set and get method. So that's the whole idea is to, for the hit collection class. So though it is said, okay, I mean, this is the thing is there. The things which is not written here is that the where you have really put the set and the get information and the set information. But that is the most important thing, okay, for the hit collection. Okay, so the hit class itself. And so what you do in the sensitive detector class. So in the sensitive detector class, okay, obviously you have to include this the hit.hh because that is where the hit has to be there, and also you have to at the end of the hit at the end of the hit, okay, you have to also define the hit collection. So all you have to say, okay, I mean, you have to say, okay, I mean, what type of hit collection you are doing, and you can see, okay, it is essentially using the templated hit collection class. So all you have to say, okay, I mean, you are essentially using the templated hit collection class for doing that. That's all is required, okay, for defining the hit collection. There's nothing more to it. Okay, so that's the only thing you have to do, okay, for that. So these are the two things, okay, which is required, okay, in the sensitive detector, the hit and the sensitive, and both are defined in the myhit.hh. Okay. Now, in the sensitive detector, you are essentially declared that your detector is publicly inheriting from G4V sensitive detector. So that's what it does, and it is usually called with the name of the sensitive detector. That is nothing but a string. Okay. The important things, okay, for sensitive detectors are the three methods which you have to do. One is the initialize. I'll tell you why. Okay, the initialize is important. Okay, because I'll come to that later on. Okay, because then you really have to get the pointer to the hit collection class. Okay, I mean the hit collection object, and so that is the done only once, and then during the simulation process, every time the sensitive the track reaches the sensitive detector, and that is a step takes place in that thing. It calls the process hits, and the argument for the process hits are two things. Okay, the information of the step, the entire information of the step, and information of something which is called a touchable history. I'll talk about the touchable history in a minute. And these are the two things, okay, which is sufficient to for you to get all the information of the what you want to record. Okay, so the first thing is to get the information from the step, and the second thing is to get the information of the detector configuration. The touchable history is essentially is for the what exactly in which particular detector it has taken place, and so this is what where you do the recording in the hit collection, and this is as you said, this is your private hit collection, and at the end of the event, you have this method end of event, and in the end of event, okay, this is called the end of event in the from the event thing itself. I'll come to that again, and there it calls with the hit collection pointer, and then you say, okay, I mean, what you have to store in that in that. Okay, so that's the last thing which you have. Now, as I said, okay, I mean, there you have got essentially two types of detectors normally. One type of detector which is where you do not have in particular detector, there are not too many tracks, okay, in terms of particular detector. Okay, so these are the detectors which are called tracking type of detectors, where you in a given cell, okay, I mean, you can have entered the information only once, more or less. If there are multiple entry, obviously a tracking device cannot work. Tracking device only works on the principle of only one entry, more or less one entry for a given track. So here you have, since it is a where the number of entries is limited, obviously you are free to store more information. So there, a tracker hit typically obviously contains information from which a track can be reconstructed, and with all these attributes. For example, it's obviously the position and time. You need the energy deposition of the step, because from the energy deposition of the step you can calculate the rate of ionization loss and the identification of the track where it is, which is entered it, and some cell identifier in which, but this is geometric information where the detector, in which detector it has come to. Now, when it comes to a calorimeter, I mean, you have millions of particles are generated inside a calorimeter, so it cannot afford to store that much of information. So what it does, the calorimeter, is that it essentially it sums up all the deposited energy in that particular cell, and some timing information, and obviously some geometric information of the cell where it takes place. Okay, so I think it is a shortened thing. Okay, so I think the writing the heat sensitive detector class is a little bit more complicated, okay, for a calorimeter than for a tracker. For a tracker, the sensitive detector class can be written very simply. Okay, I mean, you store all this information and you don't have to do that. But in for a calorimeter, you have to also keep track of the history. So look at this particular cell, if something has happened in that particular cell before or not. If it has happened in the particular cell, obviously then you keep on adding the energy deposit. If it has not happened, okay, I mean, then you create a new hit. Okay, so that's why you have to do a little bit more. You don't have to do this testing on this history in the case of a tracking detector. So it is, that's why I say it is simpler to write sensitive detector for a tracking detector than for a calorimeter. Yeah, tracking detector means what? Okay, so tracking detector, you have I don't have a picture of a typical experiment. There are two ways of detection in at least in high energy physics. Nuclear physics is mostly calorimetry. Sometimes it uses tracking detector, but not so often. Okay, so it's essentially total measures total energy. What is done is that you can, if it is a charged particle, you can sometimes know information about a charged particle without really destroying it. That means, okay, you know the charged particle, you measure the trajectory, you put the charged particle in a magnetic field, the charged particle bends in a magnetic field. From the bending, you measure the momentum of the charged particle. So you have great information of the charged particle itself. The charged particle traverses, for example, in a light medium, okay, like any gaseous medium, without really doing any destructive interaction. It only does an ionization in its passage. Sometimes it knocks off an electron, which is we have an extra electron which is there, but otherwise, okay, it is what you call it is not an explosion. Okay, so for tracking detectors, okay, I mean, can work without since it works without destroying the particle. It really works in relatively clean environment. Whereas if you go to very high energies, the the magnetic field is anyway limited. You cannot go to infinite magnetic field. Okay, so if you go to a very high energy, obviously the curvature would be small, and then the accuracy of measuring the momentum would be bad. It would be very, so obviously, okay, at very high energies, you cannot measure the momentum of charged particles to a high degree of accuracy. So that is one problem. Then, but in addition to that, there are lots of neutral particles which are produced. For example, you have got photons. A very large fraction of the things goes in the form of photons. And then in addition to photons, you have got all the neutral particles, like you have got neutrons, you have got what do you call it, K zeros and things like that. Okay, I mean, there are lots of also other neutral particles which is there. So how do you handle them? The only way to handle them is that let those particles interact and destroy themselves totally. And from when they destroy themselves totally, all the result of destruction is that you go to zero energies. So the total energy is deposited in the medium, and you measure the energy which is deposited in the medium, and from that energy you could say, okay, I mean, this has happened. Now, the cell positions where the things have happened, you can trace them in a way, okay, I mean, then you can join them together and you can get a direction. So you can get a direction by joining the cells, and you can, from the deposited energies, okay, I mean, you can get the energy measurement. So that's how, okay, the other measurement is done. One is this is the calorimetric measurement. So when we are not operating up to, for example, 10 GeV, for example, the tracking detectors are the most important one, and you need calorimeters to some extent only to measure the photons and nothing else. But as the energies grow, the calorimeter becomes more and more important. Okay, so that's why, okay, we have to handle both of them. Okay, so that's.
Then in a tracking detector, is the whole volume in which the particle travels, does it need to be detailed and specific volume?
To be? No. That is not sensitive. Sensitive is the one where you are recording the information.
Then how is the trajectory recorded when that volume is not sensitive?
No, the thing is, you cannot, what is the point of recording? If you do not, the place where you record the information is a part, say for example, a gas, going through a gaseous medium, it ionizes on the way through, but you are not measuring all the ionization points. Only when it is ionization, okay, the electrons gets drifted by an electric field and collected by some other wire, okay, which is situated on the way. So only those places, those wires are sensitive. Not the gas is sensitive. So wherever you record the information, that is a sensitive part. So it depends on how you try to do that thing. Okay, I mean, you can declare the whole gas to be thing. Okay, but then you really have to really work out, okay, how exactly you model the thing. Okay, I mean, to get to the cell positions and all that. So unless you have the geometric information of identifying the cell and things like that, okay, I mean, you really have no, you cannot do that. Now, the user now comes what you can do. Okay, I mean, now one has to remember that when you are in a sensitive detector, okay, I mean, it has got has a unique detector name, okay, and that is essentially the name of the you see, okay, sensitive detector, when it's instantiated, there is a name which is given, and that name is then more or less is a unique name. Say, for example, you have got five detectors which are sensitive. So you try to give 5 different names, okay, to do that, okay, not the same name all over. Okay, so that is the thing. Okay, you have to give a name of each unique one. You have, for example, 2 sets of detectors which have its which are these dedicated sensitive detector objects. Now, the functionalities are exactly the same. So they can share the same class. Okay. So obviously, okay, the same class can do that, and there is an example there. Okay, I mean, which is an extended example inside Geant4, okay, which has provided that thing. So that is one thing. Okay, so as I said, okay, I mean, in the thing, okay, I mean, when you are instantiating the sensitivity detector, you have essentially give a detector name which is unique, and then you have a collection ID. Okay, this is the name of the identification of the heat collection. Now, the heat collection in the thing is that, okay, I mean, all it says, okay, I mean, that in the constructor, or you have to say the collection name, insert the name of the collection. It has to be defined, but now in a sensitivity detector can generate more than one kind of hits, as I said. Okay, so say for example, if you have a, I do not say, you only say that it can generate several kinds of hits inside the sensitivity detector. So you have to give the collection names of each of them. So as I said, okay, I mean, there is a method initialize in the sensitivity detector, and this initialize is required for getting an information for getting this collection ID. Now, this collection, why getting the collection ID is an important thing is that, okay, this is a very heavy operation, and that is required every time you try to record the hit. You record when you want to record the hit, okay, I mean, you need this identifier. But every time you cannot access this, you cannot get the collection ID. So it is done only once in the sensitivity detector, and that is where in the initialize method. You cannot do in the constructor because at that time you do not get this information at all. So in the constructor you cannot do it. So it has to be done after the entire construction is complete. So so it is once it is constructed and registered to the sensitivity detector manager, then only then it can be done. And so this is the only place where it is to be done. And you can say, okay, I mean, you can see the initially the collection ID is said to be negative in the constructor, and obviously, okay, when you get the initialization class, okay, you can get that thing. Okay, so and obviously then you can get the hits collection. Is that your new my hits collection? Okay, I mean, that is a thing which is defined in your hits class, and then you have the give the sensitivity detector name and the collection ID name, and this collection ID name, okay, I mean, obviously the first ID name is here. If you have many of them, okay, I mean, obviously you have to do the whole thing in a loop. Okay. Okay. Now, this is something which is obvious, okay, which you since in the calorimetric type of thing, okay, I mean, you are essentially sum of the energies for a given particular cell. It has to be inside when you first have that, okay, I mean, you have to start with 0, and then you have to keep on adding that. Okay, so there's nothing very special about it. So This is the thing which you most likely will have to do, is that it's the one where you have to have the process hits. And as I said, the process hit comes with an object of the step object and an object from the history of the touchables. As I said, okay, it is invoked for every step in the volumes. So this is the a thing which has to be written or come in with a little bit of care. Since it happens many times, okay, in a given particular event, okay, I mean, it has to be as light as you can. If it is, you do a heavy computation at this step, okay, I mean, then it is not a good thing to do. And so you try to see, okay, I mean, as I said, okay, I mean, use your computation skill, okay, I mean, to do as little things you can do in a given step. So, for example, if you have many constants to be used, let the constants to be defined in the constructor or something like that, or initialization method, and that is to be used or come in that. Try to avoid division. Try to use multiplication as much as you can. All the tricks, okay, which normally have, okay, we'll try to utilize that, okay, in the processes. Now, the one thing is that, okay, I mean, you have two sets of information in a given step. One is called a pre-step point, and there is a post-step point. Okay. Now, when you, if you want to get what happens in the post-step point? Post-step point has information of at the end of the step. Whereas you are recording the information of a given step, which is at the pre-step point. So if you want to get the information of the, for example, for the position and things, you have to get it from the pre-step point and not from the post-step point. And if you want to get the, for example, the track momentum, you don't go to the track itself. The track contains the track momentum at the post-step point. You have to go to the pre-step point and get from the pre-step point to get some reference to get the track momentum. Okay. You can see that the process hits has to return a boolean, and usually, okay, you just say, okay, I mean, return true. That is good enough. It does not utilize anywhere in the Geant4 code itself. And this method is invoked at the end of processing an event, and it is essentially to clean up the things, okay, for the next event and so on and so forth. Okay, so that's what is done. Now, as I said, okay, the some of the things which I said is repeated here. The information of a step is split into two parts, as I said, in the pre-step point and post-step point. Some information you have to take from the pre-step point, and some information you have to take from the post-step point. And as I said, the position in the world coordinate system, the global and local time, the material, okay, I mean, all of them has to be obtained from the pre-step point. Okay. And if you really want to get the track momentum, also you have to. Sorry, I have to. Hello. হ্যাঁ বলুন আচ্ছা ঠিক আছে আমি পাঠিয়ে দিচ্ছি দেখে পাঠাচ্ছি Okay. Now I have to go back a little bit. What does a touchable history is? I'll go back to this example. Say, for example, you know that you have got a hit in this HSCN here. Now, HSCN is a sensitive detector for a scintillator, but it could be in this branch or in this branch, first of all. Secondly, even if it is in this branch, it has got what do you call? It has got maybe several segments, and each of these segments, okay, it has got this. So it has got 5 segments here, and then it's each of them. So only this information here, where it is not important. You have to really know the full path of the tree, okay, to trace it back. So this is essentially what is called a touchable histories. So it really constructs starting from here all the way back. So from each of them, okay, I mean, it tries to see, okay, which particular part is. So for example, this guy, okay, I mean, if you really see, may have very few logical volumes, 22 logical volumes. But the total number of touchables in this thing may be few hundreds. Okay. So I think, okay, when it tries to expand, okay, when it tries to a more complex detectors, okay, I mean, it could be millions, a few millions, okay, for touchables. So you cannot really work with those few millions, okay, in memory, okay, I mean, all the time. So this touchable history is something which is constructed only when the track is processed, and then at that particular instant, this touchable history is something which is available to the user, and from that, okay, one has to really say which particular cell you have the information in. So I think, okay, I mean, touchable and logical volume. I mean, touchable essentially points to a logical volume, but the touchable is not a logical volume. Okay, so it is something which is obviously something more than the touchable. And touchable history is a vector of this information. Okay, it knows obviously. Okay, when it goes through that, okay, when every step, okay, you know at which particular copy number you have got in the logical volume. You also know the translation rotation matrix with respect to the mother. So you can, at every level of this thing, okay, you can construct with respect to the with respect to the master, to the world reference frame. So if you have a point in a given location, you can go. When you get a position, for example, the position would be in the master reference frame. But if you really want the position in the local reference frame, you have to need a what you call a transformation matrix for doing that. That has to be obtained, okay, from the touchable. Okay. So suppose you have a calorimeter which has got 4 columns and 5 rows. Okay. So I think, okay, I mean, you have to know the row number and column number to get a unique positions. Okay. So that those things, okay, you have to really obtain, okay, to get the correct positions. So you have this implemented, as I said, by 2 levels of replica. So in reality, there is only one physical volume object for each level. Its position is parameterized by its copy number. So to get the copy number for each level of the cell when the step belongs to the 2 cells. Okay, so that's exactly what you have to do. So you have to get copy number of the for the row and copy number of the column to get a unique identifier. Okay, so the touchable is used to get the proper copy number, the transformation matrix, etc. So all the geometrical information has to be obtained from the touchable. And this I already have said, okay, that geometrical information, the user cannot get the correct copy number. The geometrical information in G4 track is identical that in post-step point, and the user cannot get the correct copy number for pre-step point if one directly accesses the physical volume. So only from the touchable history you can get the correct copy number, not from the physical volume, which you get in which physical volume is also some thing you can get from the step point, but that is not the place from where you get the correct copy number. To get the correct copy number, you have to go to the touchable. And if you have multiple, for example, level, obviously, I mean, there's no way left for you at all. So this is how you can access that. From you get the pre-step point. I think this is the method, get pre-step point. Then you get the touchable. Essentially you put touchable history star. From the pre-step point you can get the touchable, and then you can get the copy number from that. Now you have, for example, the touchable, you can see there's a get volume. Now the get volume has got essentially a index here. Now this index, if you do not give any number, it is taken as 0. Otherwise, if you get an index, okay, I mean, it says where it is. Now, as I said, okay, I mean, you have got two levels here. So I think, okay, I mean, if its index is 0, it refers to this particular. Here, this A can happen many times. It is not, when though we have drawn it once, this may be repeated maybe 20 times. Here, in B1, A may be repeated 24 times. And B1 may be repeated 6 times, and B2 may be repeated 12 times. So here you have got 12 times 20, and here you have 24 times 6 is 144. Okay, so you have got 240, and here is 144. So you have got altogether something like 384 cells. So from that you come in here, you come in, you need this information here, okay, which number it is, and also you need this information here to identify that. So to get the information of A, it is the first line is good enough. Information about B, you get the second line, you have to get that second line. Some other copy number. You can go to, it can happen or come in, there can be another step up, I mean, which is equal to C, okay, for example. So it can have a various step for doing that, okay. So you can change the things, okay, I mean, 0, 1, 2, okay, I mean, you can go up and down. Now, as I said, okay, I mean, to get the positions is that for the in the position in the world is obviously it is this just the pre-step point. You get position will give you the position in the world reference frame. Now to go to the local reference frame, okay, I mean you have to need a transformation, okay, to the local matrix. So you have to get the local position. From the touchable, you get the history. From the history, you get a top transform, and then you transform the point from the world position to go to the local position. So you start with the all world position, and from here you get the transformation matrix to go to the local position. Now, as I said, the event object has this the hit collection of this event object at the end of the event processing, where you store all the hit collections information. Now, so this is stored as the G4B hits. This is a virtual hits collection, and you have a concrete class for doing that. So if you want to get information for a given thing, okay, obviously, okay, I mean try to cast for the, since you're a user, you know, okay, what type of hit collection you want to access. You have to cast them, okay, for the concrete class before you can try to get that. So from the sensitivity detector manager, you can get the collection ID, where you give the detector name and the collection name to get the collection ID, and the index table is also stored in G4 run. Okay, so from that, okay, you can get the hit collection, and you can then from the hit collection, okay, you can get this information. So this is how you try to do that. Okay, I mean this is exactly, okay, the in the event action there is an end of event action method, and that is a thing, okay, we have to remember. Okay, that is the one where you have to do. This is the one. So you have to get the collection ID for that. So this is the detector, this is the collection, and from that, okay, you can get the information from the collection ID, and then from the get the hit collection for this event. You essentially, okay, I mean, utilize this thing, and if you the hit that is not a null pointer, you can get the your my hit collection from that with this particular ID, which is obtained here. And then once it is, this one is also valid, then obviously you can get the number of entries in that particular thing, and then you have access to all the hits which you have. So this is an important thing. Okay, at the end of the event, okay, you can get all this information of the hits, and then you can store them at that particular stage. Okay. After this, okay, we come to on the recording of the things. Okay, the next thing is important is what type of physics we will try to utilize, okay, for the simulation. And as I said, okay, I mean there are two. Well, there are all types of interaction which can take place. Okay, this which is a strong interaction, electromagnetic and weak interaction, and you have to say, okay, and each of them comes with multiple choices. For example, you have got a given particular interaction are described maybe with several different models. Each has its own precision. You have to see there's all two things. Okay, a given model is usually valid even for electromagnetic processes for a given range of energies. It's not valid for the entire energies. So to see, okay, at what energies it is important. The second thing is that the accuracy of the model. So if you want to have more accurate results, obviously, okay, I mean, it is much more expensive in CPU time. So you have to see some sort of a compromise between accuracy and the thing. That's why, okay, I mean, Geant4 does not provide you a unique physics thing. It gives you several models to you. It is up to you to choose the ones which you require according to your own requirement and make a physics list out of it. The only thing Geant4 provides you, okay, I mean, it has a recommendation of some physics list for certain applications. So, for example, if you are doing a high energy experiment, they say, okay, I mean, this two physics lists may be useful to you. If you have, for example, try to see how much activity is going on, okay, for example, how much background is created in a given place, to study, okay, what type of shielding you require in a given experiment, they try to provide you, recommend you, okay, another physics list for doing that, and so on and so forth. Okay, so similarly, okay, I mean, they provide, if you want to look the X-rays of a body, they provide you a suitable physics list for doing that. So for every application, okay, I mean, they have a physics list for doing that. So, and you basically have to make a pick and choose for doing that. So what physics list does, it instantiates the particles and it instantiates the models for each of these particular particles can take place. And then you can say, okay, at what range, okay, these particular models will be valid for. So that's the physics list does, what the physics list does. So as I said, okay, I mean, all the things are utilized by invoking the idea of what they call a process. So all the models are given, I mean, eventually give rise to process, and you can see that all the process have the same behavior. The process can be electromagnetic interaction, can be photoelectron photoelectron hadron interaction, hadronic interaction, decay, optical interaction, parametrization, or transpirations. All of them, okay, are essentially called a process. So they have to have the very similar behavior, and that is not for the user, okay, that is for the Geant4 to handle. The behavior is similar mainly because, okay, then the Geant4 can easily write the way the transportation can take place of a particle. And there are three basic types of processes. The thing which happens at rest, continuous, or a discrete process. Discrete process means, okay, when that particular process takes place, the initial particle gets destroyed, and you have got two new particles, two or many new particles produced. Okay, so this is basically in inelastic scattering, so discrete process. Of course, sometimes, okay, I mean, discrete processes can be not non-destructive, like a Bremsstrahlung is a non-destructive process. That is also a discrete process. As I said, transportation is also, as I said, is a process. Is essentially interacting with the volume boundary. It's not really interaction with the material content, but with the volume boundary. Now, what Geant4 does, it essentially asks each of the processes which is there to find the shortest length to come in for a given particle, okay, to traverse to do that. And shortest of this, from all the processes is taken as the step length. So that's why, okay, I mean, they are declared as the things. What's the time? Now, there are several types of modules which are combined to define as a physics list. Okay, I mean, as I said, okay, I mean, electromagnetic processes, decays, hadronic, elastic, stopping particles and captures, ion nuclear interaction, step limits, and others. Okay, so there are many different things. So here we have got optical photons, exotic physics processes, thermal neutron transport models, so on and so forth. So each of these models, I mean, the physics list is constructed by through these processes. So you register physics method, you can replace a physics method or remove physics method. But most of the time you need not do any of this thing. Okay, you try to adopt one of the prescribed physics list, okay, which is given by Geant4. So for example, this is just an example of making a physics list. So here you say, okay, you declaring first, for example, EM physics. So you register physics, which is a EM standard physics with a given verbosity. So that is the registered physics is there. Now, if you have a synchrotron radiation and a gamma nuclear processes, okay, so this is there's a thing is called EM extra physics. So that you can define, and that you can do a registration of that. So you can put this part in itself here rather than in two steps. Okay. For example, in decay, you need not have this dash. Okay, I'm saying all these things are identical. Okay, if you do not have this arrow, it does exactly the same thing as this registered physics. And you need not have many steps. You can declare the whole thing in one thing. Hadron physics is done in one particular hadron physics model. Stopping physics, ion physics, neutron tracking. But this is an example of making a physics list. Okay, so I think essentially just register physics is a thing which is there. But I think I just giving you to for the sake of completion, you need not have to do that, and you can take a existing physics. I'm existing physics list to do it. Just to see how detailed the whole thing is. There you have got all these processes, which is there. The models are applicable for electromagnetic physics for the multiple scattering. Bremsstrahlung, ionization, annihilation, photoelectric effect, Compton scattering, pair production, Rayleigh scattering, conversion of gamma conversion, that means pair production, synchrotron radiation, transition radiation, reflection, refraction, Cherenkov radiation, scintillation. So all these processes have got a corresponding model for that. And they are applicable, as I said, to electrons and positrons. Obviously, not all are applicable for electrons, positrons. Some are applications for electrons, positrons. Some are applications for photons. Some are applications for muons. Some for the charged hadrons. Some for the charged ions. And as I said, when you work at the high energies, you can do using analytic models. So these are rather fast, but when you go to low energies, the analytic model fails, and then you have to really require data-driven models. So I think depending on where you try to make your application, you try to utilize those things. Sometimes you say, you want a simulation which is good to keV, and sometimes you say, it is good to 0.1 electron volt, the accuracy. You have to really see, what type of accuracy you really require out of a simulation. Most of the high energy physics applications are good to at the level of few electron volt. So I think for that, we do not need very all these data-driven models, or mostly we can avoid the data-driven models. So this is for the electromagnetic physics, okay? So obviously, okay, I mean, these are the options which is given for doing that. As I said, okay, I mean, you have got a fast but less precise. The second one is a less precise version of, I mean, these are the two fast and precise, not so precise version. Then you need, okay, I mean, a more precise versions. Then you go to this op3 and op4. Now, these are the variations, okay, I mean, you know, of 3 and of 4. I think these are essentially variations of the three options. They are precise. I think in some cases we are now living in our applications in high energy physics somewhere between op3 and op4. We cannot go all the way down to op4, but we take some parts of op4, okay, and mostly utilize op3. Okay. I think hadronic forest is even more complex. And here they try to divide the whole thing into two parts. Okay, one which tries to provide the cross sections, and one is tries to model the particle production. The cross sections, there are various ways of defining cross sections. Okay, I mean, there are alternatives which is given for the cross sections, and obviously the cross sections again can be defined by analytic methods or by data-driven methods. Okay, so when you go to real very high precision thing, okay, I mean, analytic method fails. You have to go to the data-driven methods. Okay, so I think, and you have things for fission, capture, elastic and inelastic cross sections. Okay, so I think so. What is possible is that you can load different sets of cross section, and depending on your energy, okay, it picks it up. Okay, whatever it is. For example, if you have energy here, okay, it obviously picks up set 3. If your energy is here, okay, I mean, obviously it picks up set 4. Okay, so if his energy is below this, okay, I mean, it picks up set 1, and if it's at the very high energy, it picks up set 2. So it depends on what the thing. Okay, I mean, it does it. It is rather flexible, and the same thing is true for the models. As I said, okay, there are 3 types of models. The thing is, okay, I mean, there are theory-based models. That means, okay, it comes from some sort of theoretical ideas, not really from the first principles. There's no first principle models is good for high energy physics, for the strong interaction. First principle models are good for the electromagnetic physics or the weak physics, but not from the strong interaction. As soon as the strong interaction, the first principle things, okay, are work in the at very high energies, but as soon as you formation of hadrons come in, all the perturbative method fails. Okay, so it becomes in the non-perturbative domain. Okay, so I think, okay, these are really models. Okay, I mean, which comes motivated by some first principles, but not really first principle things. Okay. And these models are for the string excitation, internuclear cascades, or the nuclear evaporation fission models, and their validity at high energies, medium energies, and at low energies. So these are the three things. Then you have a parameters model. That means, okay, this is not really comes from this. Okay, derived from the data, but not really taking the data itself, but some sort of parameterization in between. They're rather fast, but not very accurate. But if you really want to look at very precision thing at the low energies particularly, you really have to go to the data-driven models. So I think, okay, I mean, what is normally done, okay, the high energies, okay, I mean, you go to the theory-based models, and at very low energies, you have to go to the data-driven models. Okay, that is the combination which is normally done. Now I just did this. Hello. আবার আচ্ছা ঠিক আছে পাঠাচ্ছি sorry for this I think I have to stop here. Okay, I have to go back. I think I'll basically stop here. I'll not do anything next week. I'll do only on the 28th. That means in 2 weeks from now, Wednesday at similar 1 o'clock. I think 2 of you will be here, I think. So you have to set up the things for the others. Do you think they joined? Huh? Okay. 28th, yes. 1 o'clock, huh? Yeah. Yeah, because 28th they have a